Hey mathletes, we're looking at vector application, angles between lines, and constant velocity problems. It's C and D out of chapter 13. So here we go. We want to be able to find the angle between two crossing lines, right? Or two parallel lines, I suppose. We've already done this with vectors, right? And a vector, several vectors, an infinite number of vectors make up the any line. And so all we have to do is look at those are the directional vectors, right? There's a slope essentially. So all we have to do is to find the angle between the two lines, we have to just take the two directional vectors and throw them into the equation we already know for finding the angle between regular vectors, right? These are just an infinite series of vectors. When we use this, you'll take the inverse cosine and you'll find an angle theta. We and you nerds have decided that we're going to use, when we talk about the angle between lines, we're going to talk about the acute angle, just FYI. So one thing to consider is if they're parallel lines, the slopes of them are going to be equal, if not simplified. So this might have a direction vector, right? And this will have a direction vector, and they'll be similar, but they'll be a scalar multiple apart, right? So this might be 1, -2 goes over and down, right? And this would be 2, -4, right? Which is essentially 2 times this direction vector, 1, -2, right? And so you can say, hey, look, this and this are the same. They're just a scalar multiple, so they must be parallel. Likewise, perpendicular lines have the property that one direction vector has no component in the other's direction vector. So the dot product of the two direction vectors, b1 and b2, should be 0, right? Two ways to think about that, one of which is you can use the equation that we've been using before, that the magnitudes times the cosine of the angle in between, or you can add up the product of the x, y, and z components, depending on what you're given. So let's try 2 examples to check that out. We'll do both of these on separate pages, so let's just jump ahead. So this is example 5 from that previous page. They say find the angle between the two lines, and they give you this as line 1. Well, actually, I should probably make it in black, huh? That's kind of obnoxious because it's in a parametric, so it's a little easier to see it in vector form. So if you take the 2, you start at 2, 1, that's this piece, right? And then you move t, every t, you move -3, and this 1 that's implied in front of here, -3 and 1. So we went from parametric to vector form, and we did the same thing with this second line, right? We start at 1, -4, that's our position vector to get to the first spot, and then we move every s, we move 2 over and 3 up to 3, right? So there's our 2 vectors, right? And so they're crossing, but really the only important piece is how they're moving, right? It's just the slope, and we can tell just by the slope their angle between them. So these are our 2 direction vectors, and we can just use the equation that we've been using before, which is the dot product divided by the product of the magnitudes. So this is the dot product. It's 3 times 2, right? That's this, plus 1 times 3. That's this. So -3 times 2 plus 1 times 3, right? Make the sound effects if you like. And then over the magnitudes of each vector. So find the magnitude of this one, right? The magnitude is -3 squared plus 1 squared, and the root of that. So that's this 10, and then it's a product, so multiply by the magnitude of this, which is 2 squared plus 3 squared. Right, so 9 and 4, 13, take the root of that. So once you crunch all those numbers, you end up with cosine is 0.26, and you take the inverse cosine, 75 degrees. Cool, cool. Similar example, find the angle between these two lines. They're three-dimensional lines because they have 3 dimensions. And what's nice about them is they're already given to us in vector form, so we don't really care about this initial position vector. All we're interested in is this direction vector. And lo and behold, hey look, -3, 1, 1, -2, -2. They're moving in the same direction even though they're not starting in the same spot. So I don't know that they're not necessarily on top of each other, but they are moving in the same way. So they're parallel because they have the same direction vector or a scalar multiple thereof. Cool. All right, let's give it one more shot. So I want the measure of the acute angle between this line and that line. We could plot them, right, and we could measure them, but let's first try to find the gradient and the direction vector of line A, right? So let's give this a shot. If we take this, I guess we're calling line A, and we'll call the other one line B. Wow. And you move this around, you rearrange this, you can solve this and solve for y. Move 2 over here and 2x plus 5, right? So this is the slope, this is the gradient, it's -2 over 1. So this is, if you remember your algebra, this is rise over run, right? So you could say it rises -2 and it runs 1. Well, in the direction vector, this is the x change and this is the y change. So all you have to do is take your slope and flip it upside down, right? -2 and 1. Great. So that's the gradient for this, right? So A has a gradient. A has a directional vector of 1, -2. Try the same thing for B. Go. All right, if we clean B up, B does the same thing. We have to clean up this mess. And you subtract 3x, and there's the 8. Divide by 2, so it looks like the slope is +3/2, right? So this is change in y over change in x. This is change in x over change in y, and so you just flip it over. So this has a direction vector of 2, 3. Great. And then we can find the angle between the lines using our fancy equation. Yeah. So we can say, let's take the dot product of our direction vectors. So we take the dot product of this. We say 1 times 2 plus -2 times 3, right? And then we take the magnitude of this, 1 squared plus -2 squared. That's this piece, right? And then we take the magnitude of this, 2 squared plus 3 squared, and we crunch the numbers. That's cosine of theta. So then you take the inverse cosine of theta, you get around 60.3. Cool. All right, one last application problem, constant velocity problems. That's the Flash. He gets constant. He has constant velocity problems. Get it? Get it? All right, so here's a boat moving. It has an initial position from the lighthouse. It's a certain distance away to start with, and it's at that spot, and it's moving in a constant velocity, right? So here's its location. It's 2 kilometers east and 20 kilometers north, so this is 2, 20, right? So this position vector to get there is 2 over 20, right? Like that. All right, and the boat is heading 4 kilometers east for every 3 kilometers south as you travel. So it goes 1, 2, 3, 4 over and 1, 2, 3 south, right? So this is its direction vector. I might call it D. All right, so the position vector we figured out is 220. I guess it should be vertical. The direction vector is 4, -3. And then so the equation describing the path is just, well, the vector to get us up to where we start, right? This gets us up to where we start, and then for every t we change in this fashion. So this gives us our direction vector. They're asking for our overall speed, and the overall speed is just the magnitude of the direction vector. It doesn't matter where we start, it just matters how we're moving, right? So the overall speed is the magnitude of the direction vector, which is root 4 squared plus negative 3 squared, right, which is 16 and 9, which is 25. So this ends up being root 25, which is 5, right? Plus or minus 5, but we're just assuming that wherever you're facing is forward, so positive 5. Cool. Try this one on your own, and I'll run through it with you. It's the same sort of idea. Tell me where it is at time t. Go. Okay, so we've got an object that's initially somewhere. It's at 5, 10, 1, 2, 3, 4, 5, 10 there, and it moves with this vector, right? It moves at 3 and negative 1. So essentially it's doing 1, 2, 3, and negative 1. It's doing that. Yeah. Fine. All right, find the position of the object at time t. Well, that sounds like an equation to me because we don't know time t. Oh, there's a fancy drawing just like I drew. I do know we want to make an equation, right? It's going to be in vector form. So the x and y positions are based on where you started, right? Which is the position vector, the initial position vector is 5, 10. Go over 5 and up 10, and that's where you start. And then every t, you move in this direction vector, right? Just like we were saying over here was 3 and negative 1. And then if you want to crush it into a little more beautiful equation, this is fine too. I kind of like this better, but so after t minutes, the object, this is parametric now, is at this point for the x and this point for the y based on t. All right, I wish they would have given us more stipulations about what form they would have wanted that left at, but there you go. Giving the speed of the object, well, speed of the object is just the magnitude of that. So it looks like 3 squared plus 1 squared, so root 10 meters per minute. Fine. Give us the position at time t. Well, at time 3. We'll take t equals 3 and plug it into there and there, right? So you get 14, right? So let's see, 9. Yeah, I got 14 and 7. So its position is at 14, 7. And then, find the time when the object is due east. Well, I don't know where that'll be, but if this is moving, when it's due east, this position is something for x and 0 for y, right? So we can take this y equation. This is really y equals 10 minus t, and we want to know what time is y0. So you could just solve for that. So 10 minutes. So you add t to both sides and get 10. Great. Alrighty. We'll see you in class, and these are the problems we'll attack. Ciao.